So, we were working on the Thevenin and Norton theorems, Thevenin's theorem, Norton's theorem, right. And both of the theorems were kind of at the same time historically. What Thevenin says is, if I have a network n, then let me do two experiments. Experiment 1 is I measure the open circuit voltage, experiment 2 I measure the driving point impedance. Okay. Driving point impedance is a special word, new word. What does it mean? Driving point impedance means I switch off is also a new word. I switch off all the independent sources inside my network. I apply a voltage, measure the current from outside, or I could push a current, measure the voltage, either ways. Okay. The sentence switch off all independent sources, be careful whenever you want to switch off a source, it is not really a switch like this switch over here, not a light switch, not that kind of switch off. Switch off over here means make it 0. So, a voltage source switch off means it becomes 0 volts, which effectively means the voltage source is short circuited. A current source 0 amperes means make it open circuit. So, all voltage sources, independent voltage sources, not dependent, only independent voltage sources you short circuit, independent current sources open circuit, then apply a voltage outside, measure the current, or apply a current outside, push a current into the circuit from outside, measure the voltage. Okay. This is Thevenin's theorem. Norton's theorem is very similar. He says that instead of measuring the open circuit voltage, I am going to measure the short circuit current using an ammeter. And then what Thevenin says is, with these two experiments, I am going to represent my network as open circuit voltage V t in series with Z t, the driving point impedance. Norton says that instead of the network, I will have short circuit current I n in shunt with Z n, the driving point impedance. Fine. And now, what we are going to do is, we are going to prove these, and the proof is pretty similar for both. We will do one, you can outline what the other is going to be. So, let us try Thevenin. And what we are going to do is, this is my network, and inside the network we have, of course, we have only LTI components. So, L, C, R, M, all these components are there, but in addition to that there are all these sources, right. These could be voltage sources, current sources. Let me draw them a little bigger. Okay, all these sources are there. They could be voltage sources, they could be current sources, these are all independent sources, right. So, I have labeled them as U 1, U 2 all the way till, let us make it U k, not n. All the way till U k. Fine. I also have a port over here, right, and across this port we were planning to measure the open circuit voltage, and we were planning to push, right, a voltage, push a current, measure the voltage, all this stuff we were thinking of doing, right, for the Thevenin experiment. Okay. So far so good. Let us now push a current from outside. Okay. I am going to push this current I t from outside into the circuit, and let us label this voltage as V x, unknown. All right. I am going to try to work out what is V x. This is my plan. I want to work out what is V x. Now, to work out what is V x, we are going to use your favorite method, mesh method, node method. What is your favorite? Mesh is your favorite. Okay. We will use node method. Okay. We will not use your favorite one. We will use node method, because node method works happily with current sources. Okay. Mesh method, there is a little trouble with current sources. You remember? Since I am planning to push a current I t, I am going to use the node method, not the mesh method. Okay. You could have used mesh method also, but I am going to use node method, because that is what I like. Arbitrarily, let us ground this point, and the voltage, here the voltage becomes V x, correct? Correct. I mean, potential difference earlier was V x, now that voltage is V x. All right. Now, let us try to solve this using the, let us assume we are solving this with the help of node method. How are you going to solve? You are going to write it up as some matrix times a list of voltages, and that is going to be equal to some stuff, correct. This list of voltages would be all the different voltages inside, let us say V A, V B, these are all the nodes inside the circuit, right, and let us keep V x as the last node. That is also a node, V x is also a node, that is the last one, fine. And this matrix you are going to write out, correct. Now, on the right hand side, what is going to happen? By the way, what are the dimensions of A? Node voltage method, 1 by resistance, conductance, these are all conductances. Why? Because node voltage method is a bunch of KCLs, right. Every row in the node voltage method is a KCL, you are just doing KCL, KCL, KCL. Okay. So, we are only doing KCLs, which means that these are all going to be right hand side, all right hand side, all are going to be currents. So, for example, if you had U 1 as a current source, then this would probably be U 1 or minus U 1, right. And if U 2 is a voltage source, then this is probably some conductance times voltage source will come to the right hand side, correct. And there could also be some zeros in between. In fact, remember while doing the node voltage, most of those, especially those which did not have any source involved, those KCLs which did not have any source, on the right hand side you would get zeros, nice clean zeros. So, you will have zeros, and then all these U 1, U 2 all the way till U k, all of them will come Will they be in A? Will you have the U's participating in the A matrix? No. You will certainly not have any of the U's participating in the A matrix. Okay. All the U's are going to go to the right hand side. All right, no U's are involved in the composition of the A matrix. Then there is one more source. So, all the way till the kth source you are going to have on the right hand side, but there is one more. Which one is that? IT. IT is also a source, right. Where is that going to participate? In the last KCL. Okay. The last KCL is the last row. So, in the last row IT you will have a minus IT on the left hand side. So, in the right hand side you will have IT. Fine. So far so good. Okay. Next, what is the next step? What do we want, by the way? What is the objective? Why are we doing all of this? We want to find Vx. Okay. Yeah. So, what is the next step? Find the inverse of A matrix, multiply left side right side by the inverse of A, and once I do that, this is what I get. I get V A, V B all the way till V x. This is equal to A inverse times alpha 1 u 1, alpha 2 u 2 dot 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 alpha k u k, and then finally I t. All right. Okay. Now, V A, V B, all of these are not really of our interest. We only want to worry about V x. Okay. So, we only want to find out V x, only the last entry. Okay. Now, A inverse, A is a matrix full of constants, right. A inverse is also full of constants, and how many are there, by the way? What is the size of this? If the circuit had capital N nodes, how many rows, how many columns? N nodes, one node is ground, N minus 1. Okay. So, we have N minus 1 rows, right. V A, V B, V A. So, all of this also there is this. Yeah, V x is one of those only. Okay. Let us not worry about the count. The row, the last row of A inverse, Okay. It is full of some constants. So, let us say that the last row of A inverse. So, V x is going to be the last row of A inverse, maybe it is beta 1, beta 2 dot 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 all the way till beta n minus 1, fine. That is the last row of A inverse times alpha 1 u 1 dot 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 alpha 2 u 2 dot 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 alpha k u k and then I t. Is this okay? So far so good. It is just we are just writing it out, putting our thoughts on paper. This is the overall scheme of things, and if I expand it out, what do I get? I get beta 1 alpha 1 u 1 plus term by term, right, maybe something beta times alpha 2 u 2, right, and then finally beta n minus 1, which I am going to put on another row times I t. That is the last term. Fine. Now, what we are going to do is, we are going to break this up into two parts. This result we are going to break up into two parts. The first part contains all of these, and the second part is just this one. So, what have I got so far? I have got the following. I have got V x is equal to this is what I have got. Okay. Now, what happens when I measure the open circuit voltage? I t is set to 0. So, when I t is set to 0, what is V x going to be? It is going to be these, right. So, this is nothing but open circuit voltage, fine. Then what happens when I switch off, and when I say switch off, I make values equal to 0. What happens when I switch off all the independent sources inside the network? That is, what happens when u 1, u 2, u 3 all the way till u k, they are all equal to 0. What happens? All of these first set, the first set becomes a nice clean 0, and I am left only with this. All right. So, I have got two parts. First, I have got V x is nothing but V o c plus beta n minus 1 I t, right. V o c is 0 when all sources inside are 0. Independent sources. Correct? So, how do we find out the driving point impedance? We make all the sources inside 0, then I push a current from outside, let us say I am pushing I t from outside and I measure V x, and what is the driving point impedance? What is that value going to be over here? Beta n minus 1. This is nothing but my driving point impedance. Correct? Just that factor beta n minus 1, whatever that is, right. Long history is there, but whatever that is my driving point impedance. Fine. Okay. Let us now see what Thevenin wants us to do. Thevenin says, let us make VOC over here and let us make this driving point impedance ZT. What is going to be Vx now? Suppose I push some current. How much? Why should it be minus VOC? You take the drop minus VOC. Which way are you going? Yeah, so you go with IT times ZT. So, Vx is equal to IT times ZT plus VOC, drop is VOC. Okay. So, how do these two equations compare? They are the same. Right, Vx was equal to VOC plus beta n minus 1 times IT, right, and we have got exactly the same result, right, just that ZT is beta n minus 1, that is all, and VOC is equal to that junk, right, lots of that junk that you had written, all I invented all the terms, added them all up, put all the junk together, that is your VOC. Fine. So, this is the proof for Thevenin's theorem. So, I mean this is basically the theorem, right. Norton's theorem you can prove exactly in the same fashion, but do not use. So, for Norton's theorem you have to apply a voltage source, do not apply a current source first of all, and then use mesh method, do not use the node method, because when you work with voltage sources mesh method plays better just for that reason. So, use mesh method, apply a voltage source outside, with Norton's theorem you will get exactly the same, it is exactly the same procedure, the dual procedure. Fine. Okay. So, Thevenin says that any network I take linear time invariant, right, any network I take, I just measure the open circuit voltage, I call it V t, I measure the driving point impedance, I call it ZT, and the network is now the same as this, right, they are equivalent. Norton says that the same network, I measure the short circuit current, I measure the driving point impedance, and they are the same. So, let us start with a battery, a real battery, right, one which is practical, not a ideal voltage source. You could use Thevenin, you could use Norton, there is no choice to be made, right, both are equally good. So, even when you physically have a battery, you think it is a voltage source, but Norton says no, it is a current source. What is it actually? It is a source of power. Okay, a battery is a source of power, it is a source of energy, it is where energy has been stored and now you can draw power. All right. So, if you want to look at it as a voltage source, it will come with some problems. If you want to look at it as a current source, it will come with some other problems, right, in terms of resistance. But in any case, it is a source of power. Fine. So, all these sources, all these practical sources, they are all sources of power. The ideal voltage source and the ideal current source, they do not exist. Thank you. Fine. All right. So, VT ZT, I could find the short circuit current for this also. What is it? VT by ZT. And driving point impedance, what is the driving point impedance for VT ZT? ZT is the driving point impedance. So, the Norton model for this is VT by ZT in shunt with ZT. Right. Notice the arrows. When you measured the short circuit current, the arrow was pointing downwards, right. Here it has to point up, because if I measure the short circuit current over here, I need that current to go downwards. All right. So, keep in mind, when you measure the current downwards, the current source is going to point upwards and vice versa. All right. Similarly, I could start with a Norton model. This is the Norton model, right, and I could choose to apply Thevenin's theorem on this, measure the open circuit voltage. What is it? I n times Z n. So, I could say that the Thevenin model for this Norton source is I n times Z n in series with Z n, which is the driving point impedance. Fine, Z t and Z n are the same. All right, any questions? So, this is called a source transformation. Any source can be transformed into a voltage source in series with a resistor or into a current source in shunt with an impedance. Okay. Any source could be transformed either this way or that way, both are valid. All right, these are source transformation pairs, what you have over here, right. These are the same thing. All right. Now, with this we are going to do an example. Which circuit am I drawing? Wheatstone bridge, very good. Okay, so it is your favorite circuit, huh? Is your favorite circuit. Okay. 1 ohm, 2 ohms. So, you what you did not do, I am going to do. You did not do this, right? Yeah, this one. No one has done this, even though it is your favorite circuit, right. You carefully avoided this situation. Yeah. All right. So, we are going to do this. So, let us say the voltage source is 21 volts. All right, this has to be solved. How are we going to do this? So, here we are going to take the help of Thevenin and Norton, right, any one of them, right, they are all the same. So, Thevenin and Norton are going to help us over here. So, first the way we are going to operate is as follows. First we are going to redraw this circuit by pulling out the 5 ohm resistor. Just by the way, if the 5 ohm had not been there, could you solve the circuit? Yeah, it is trivial, nothing much. Okay. So, we are going to pull the 5 ohm resistor way outside, all right, and this is going to be our box, Thevenin's box. Okay. Thevenin has a box with a port sticking out, remember, he had a network N with a port sticking out. So, this is that network N with a port. What is a port? Pair of wires, okay. Pair of wires is a port. So, port is sticking out, this is the network that we have, all right. This is what we are going to analyze, and initial analysis we are only going to look at the network, and we are going to forget about the 5 ohms, because it is outside the box. Okay, let us keep 5 ohms outside the box. By the way, what is the question over here? The question is find the voltage across 5 ohms, typical question, right, or find the current in 5 ohms, whatever it is. Okay. So, we have pulled the 5 ohms outside and then we have cut the wires, and now we are going to model this box with the help of Thevenin. Okay. What is the model going to be? First we need to find out the open circuit voltage, two experiments, open circuit voltage, driving point impedance, right. Let us do open circuit voltage first. Before I do open circuit voltage, let us yeah, it is okay, ground one of the wires maybe. Which wire do you want to ground? Let us ground this wire. Just for fun. Okay. So, that node is at 0 volts, this node is at 21 volts, right. And what is the junction between 1 and 2? How many volts? 14 volts. And what is the junction between 3 and 4? 12 volts. So, what is VOC? Done. Okay. First experiment is done. Next experiment, is that I am going to first switch off all the independent sources inside, which involves making the 21 volt source a dash short circuit. So, I simply short it off, which effectively means I connect these two together, and then I look in to the circuit from outside and measure with a multimeter what is the resistance, or I could provide a voltage and measure the current, whatever works, right. You will find that measuring the resistance is just as easy in this case. What do you see? 1 and 2 are in parallel with each other, and 3 and 4 are also in parallel with each other, and these two combinations are in series with each other. So, your answer is 1 in parallel with 2 plus 3 in parallel with 4. Okay. So, 1 in parallel with 2 gives you 2 by 3, 3 in parallel with 4 gives you 12 by 7. So, 2 by 3 plus 12 by 7, what do you get? 50 by 21. Fine. Now, our model is built and we bring the 5 ohm resistor back into the picture. Where was the 5 ohm resistor? Between at this port. And now, this problem is straightforward. So, your answer to your question is 2 into 5 divided by 5 plus 50 by 21, whatever that is. Huh? How much? 41 by 31. 42 by 33. 31. Okay. Is this understood? Any questions? Followed? Is it good? Shall we move? All right. So, this is I just did a trial example of Thevenin's theorem, Norton's theorem also, it is very similar. Just a warning, Norton is more used. Okay. So, so far we have done most of our theorems, all except the last one. The last one is the maximum power transfer theorem. We are ready to do this last one. Why we are ready? It is because you have already observed that what you call a voltage source is not really a voltage source, it is a power source. Okay. So, the question in front of you is that what is the maximum power that I can transfer out of a source, that I can draw out of a source. So, if I have a power source, what is the maximum power that I can draw from it? All right. And of course, in your mind you know kind of the answer. Uh, all these power sources are basically energy conversions, right. As much power input, you can't really draw more power than what has gone into the source. So, maybe it is a thermal power plant. If I burn so much coal, then I will get so much electricity. I can't get more electricity than what I have, the amount of coal I have burnt. Okay. So, there exists a maximum, we are clear with that. But in terms of the electrical network also there exists a maximum, and that is what we are going to look at right now. So, suppose I have a source V s in series with Z s. Okay. The question at hand is what should be Z L such that I draw maximum power out of this source. Where, which is the source by the way? No, that is not the source. The source is this whole thing. This whole box is the source. All right, Zs is part of the source. It is integral to the source. It is inside. Just like the battery, what resistance? Internal resistance of the battery. Zs is just like that. It is the internal impedance of the source. Okay, it is part of the source. So, always be careful over here, right. The question to ask is always what is ZL, never ask what is ZS. Okay, you are not allowed to ask what is ZS. If you ask what is ZS, what is ZS for maximum power? 0. All right. I make ZS as small as possible, I make ZS 0, then I can draw as much power. In fact, I can draw infinite power from this source, there is no maximum. Okay. If Zs happens to be 0, there is no maximum, you can draw infinite power. Remember, we have done this in some class long back. Okay. So, never ask what is Zs. All right. The question is always what is ZL such that I draw maximum power from the source. All right. How are we going to do this? We are going to do this as follows. First of all, what is the current? Vs divided by Zs plus Zl. And what is this voltage? Yeah, but do voltage division, you might be easier. Vs into Zl by Zs plus Zl. okay, that is the voltage. And therefore, what is the power? How do you find out power? How do you find power? Wrong. These are all phasors. How do you find power? I star, conjugate of I. Remember? Okay, it is not V times I, it is V times conjugate of I. Okay. So, this is V times I. But I needs a star on top. Fine. This is equal to, what do you see? V s and V s star, mod V s star, mod V s squared, and Z s plus Z L is there in the denominator. Z s plus Z L conjugate is also there in the denominator. What do you do? And then in the numerator we are still stuck with 1 Z L. But this is the complete complex power, right. What is the real power? Active power. What is the actual power? Real part of this. So, instead of Z L, this is going to be real part of Z L. Okay, great. Now, let us say that Z s is nothing but R s plus j times X s and Z L is R L plus j times X L. Fine. Now, therefore, what is the power? What is the power? Yeah, mod V s squared divided by Z s plus Z L. Z s is R s plus R L. Sorry, Z s is R s plus j x s. Z L is R L plus j x L. So, Z s plus Z L mod squared is R s plus R L whole squared plus X s plus X L whole squared. Fine. And then real part of Z L is R L. So, let us call this P. And P happens to be a function of two variables. Which are the two variables? R L and X L. Fine. The power is a function of two variables R L and X L, and we have to maximize the power. So, to maximize the power, what do we have to do? We have to find the partial derivatives of P with respect to. So, I have to write dou P by dou R L and I have to find out dou P by dou XL. These are the two things I have to find, okay, and equate these two to 0. That is the job. So, how is this done? I have something divided by something, numerator divided by denominator, and therefore, denominator square comes in the denominator, and what happens to the numerator? Numerator into derivative of denominator. So, I get R L into what? 2 times R s plus R L minus 1 into R s plus R L whole squared minus x s plus x L whole squared, and this whole thing is equal to 0. Fine. Okay. Second one, denominator squared is there, and then I have dou x L, right. So, I get R L into 2 x s plus x L minus 0. The whole thing is equal to 0. Fine. So, what do you see from the second equation? What can you infer from the second equation? So, I can infer that x L is equal to minus x s, and as soon as I make this inference, what can I say about the first equation? This term drops out to 0, because x s is equal to minus x L is equal to minus x s. Fine. And therefore, what can I say from the first equation now? 2 R L is equal to R s plus R L, which means that R s is not equal to R L, R L is equal to R s. Okay, I want to be specific. Okay, do not write it the other way around, because it you are answering the wrong question. Okay. So, this is my solution, R L is equal to R s and x L is equal to minus x s, which basically means that Z L is equal to complex conjugate of Z s. Fine. So, whenever Z L is the complex conjugate of Z s, I expect maximum power to be transferred out of the source. How much is that power? What is the value of that power? How much power? This much, right. Z s plus Z L is now going to be equal to how much? If Z L is conjugate of Z s, 2 times R s. So, I basically get maximum power is equal to mod V s squared divided by 4 4 RS. Fine. Okay. So, if I give you, so this is called, just by the way, this P max, this has a name, this is called the available power. All right, this is the available power of any power source, right. You take a power source and you can ask the question, what is the available power of this power source? This is the available power, mod V s squared by 4 R s. Fine. So, for example, if I give you the, if I tell you that here is a source of power, here is a, I do not know, thermal power plant, the available power is so much, the voltage is so much. Will you be able to find out the source impedance? Yes, no, maybe? Qualified, yes? You know the voltage, I give you the available power, will you be able to tell me what is the source impedance? Xs is unknown. So, it is a qualified yes, you can only find out Rs, right. The resistive part of the source impedance you can find out, Xs is unknown still, Xs is you have to figure out Xs using some other method. Fine. Alternatively, if I tell you the available power and if I give you the value of Zs, if I give you Zs and if I tell you that this source has so much available power, will you be able to say what the voltage is? Magnitude. You can always refer it to 0, right. You will be able to find out what is the voltage. Does it matter if this is a Thevenin model or a Norton model? What is going to be the difference if I move to a Norton model? The only difference is going to be here, instead of Vs, it is going to be Is times Rs. Okay. So, that is the only difference. So, you have to transform the source, right, or you could build this all over again. It is not too difficult, right. You could build the result all over again. You will get the same answer, that the load impedance has to be equal to conjugate of Zs. That answer is going to be the same. Does not matter whether you do Thevenin or Norton model for the source. All right. My last comment is, what are you going to do? So, let us just think of the linear. Suppose I have a DC source, okay, Vs and Rs, all right, and I want to draw the IV characteristics of this. So, if the voltage over here is 0, what is the current? Yeah, what is the current? Vs by Rs. So, if the voltage is 0, I have Vs by Rs. If the current is 0, Vs, right. In between, what is going to happen? linear, I and V, it is a linear function, right. So, in between I expect a straight line. Okay. Now, if you want maximum power out of this is your V and this is your I, right. If you want maximum power, if you want to draw maximum power, then what do you have to do in this graph? I have to draw the largest possible rectangle underneath this straight line, okay, the largest possible, and that largest possible rectangle is right over here, right. Graphically, this happens to be the largest possible rectangle in terms of area, right. There is no rectangle larger than this. How do I know that? Do I know that, or am I just guessing? You basically have to do congruency, right. This has to be the midpoint, this has to be the midpoint, right. You have to do congruency, this triangle will be equal to this triangle, this one will be equal to this triangle, right. No, you have to proceed along these lines, and then only you will be able to prove that this is the largest possible. Let us say that you have this great solar cell, okay. So, popular choice of a power source, right. You want to draw maximum power out of the solar cell. The solar cell is not a linear device, okay. It does not, it's this IV, this straight line, that nice straight line that I have drawn over here, this is not going to happen when it comes to a solar cell. So, when it comes to a solar cell, it has a diode inside, by the way, it is a PN junction, right. Solar cell is a PN junction, there is a diode and there are some diode characteristics that are going to come up. Okay. You are aware of diode characteristics, exponential and so on. Okay. Nevertheless, this is going to be the characteristics of the solar cell. And now, the question is to find the maximum power. How will I draw the maximum power out of this? What do you have to do? You have to simply draw this curve and figure out which is the largest possible rectangle under the curve, right. And you have to do it graphically. In this case, doing it graphically is the easiest. In this case, you basically have to figure out that this is the largest possible rectangle, and then accordingly you have to decide that therefore, for the load, this is my voltage and this is my current, and therefore, my load needs to have so much resistance. Okay. So, you are basically deciding the value of the resistor. Fine. Any questions so far? So, I basically graphically have to draw the maximum, the largest possible rectangle underneath the curve. Now, once you do that, once you have drawn the largest possible rectangle, you have got a voltage V L and you have got an I L. And now, you know that you have your solar cell, this is your solar cell, right. You want to ensure that this voltage is V L and this current is I L. How will you do that? by placing an appropriate resistor over there, right. So, that resistor is going to draw the maximum power out of this source. So, accordingly you can partition the source. All right, any questions? So, we have done quite a bit. We have covered all the theorems that we want to cover. We have covered Telegan's theorem. Telegan's theorem is valid for all sources, all circuits. Then we have covered reciprocity theorem, right, valid only for LTI passive. Then we have covered Thevenin Norton source transformations, superposition before that. Superposition is valid only for LTI circuits, right. Then Thevenin Norton also valid only for LTI circuits, and then finally maximum power transfer. Fine. So, let us stop here.